Welcome to Balancing Redox by Half Reactions in Basic Solutions. For this lesson, it'll be helpful to be familiar with the process for balancing in an acidic solution, because we're going to see that there's a lot of similarities. Here we have a reaction that takes place in a basic solution. We can see that there's a base right here, chromium 3 hydroxide, or we could also be told that this is just a basic solution. So those are the two common ways to figure out whether or not a redox reaction is taking place in a basic environment. Now, as we go through our process for balancing this redox reaction, you're going to see that there's really only one difference when dealing with a basic solution compared to when we were balancing with an acidic solution. They're pretty similar, but we still start off the same way. We start off by writing our half reactions. So we're going to have a selenium half reaction, and we're going to have a chromium half reaction. So in this chromium hydroxides have a -1 charge, so this is a +3 chromium. And remember that for balancing by half reactions, we basically disregard any waters, hydrogen ions, or hydroxide ions that show up in this reaction. So my half reaction is really just going to be Cr+3 to chromium. Now, as it turns out, if you leave the hydroxide in there, it's not really going to change anything for your final answer. But doing it this way keeps the half reaction a little bit cleaner because there's less involved. Now that we have our half reactions written, our next step will be to balance for atoms. In this half reaction on the right, I'm already good. I have 1 chromium here and 1 chromium here. But for my first half reaction, the seleniums are balanced, but the oxygens are not. And to balance oxygens, it's the same as we did for an acidic solution. You add waters. So I have 3 oxygens. I'm going to add 3 H2O. Now here's where we're going to see our first difference. In the acidic solution, we normally add H's to balance out the waters. But in basic solutions, you should really be adding OH and H2O. Those are the two things you should be using to balance masses. But using OH can become very tricky because OH is not only balancing hydrogens, but you're also adding oxygens. So it can be a pain to try and add both of these. So we're actually going to use a little bit of a trick here. We're not going to add OH and H2O like you would normally use here. Instead, we're going to treat this half reaction as if it occurred in an acidic solution, meaning I'm going to add hydrogens. And I have 6 hydrogens to balance, so that's 6 H pluses. And now I can actually add OHs pretty easily, because I don't want free hydrogen ions floating around in a basic environment. That wouldn't make any sense. So I'm going to neutralize this. I'm going to add 6 hydroxide to this side, and add 6 hydroxide to this side. So what does that do? Well, these two things neutralize, so that we really have 6 waters on this side, and I have 3 waters on this side. So now I'm going to rewrite this half reaction to make it a little bit cleaner. And one of the things I'm going to do is combine like terms. So on the left, I have my 6 hydroxide plus selenium. That's going to give me on the right side this polyatomic. And now the only thing left is the waters. I had 6 on the right side from doing this little neutralization with adding H's and OH's, and I had 3 on the left side. When I combine those, essentially by removing 3 from each side, I'm going to get 3 waters left over on this side. And this reaction is now balanced for mass, or balanced for the number of atoms. So that one extra little step we added there, where I started to balance as if it was an acidic solution, and then I just neutralize all the H pluses by adding equal amounts of OH minus on each side. That extra step is what sets apart balancing basic reactions from acidic reactions. And you're going to see that every other step is going to be the same now. Given the 2 half reactions that are mass balanced or have the same number of atoms on each side, I'm now going to balance for charge. Let's do the chromium first because that's pretty simple. I have a total of +3 on the left side. I have 0 on the right side. Adding electrons will lower a charge, so I can lower this side to 0 by adding 3 electrons. Now when I go to do the same thing for the other half reaction, I have a total of -6 on the left side of the half reaction from the 6 OH minuses, and I have a total of -2 on the right side. That means the right side needs to become more negative, so I add in 4 electrons to bring it down to -6. Now that these half reactions are balanced for mass and for charge, I multiply them by each other's electrons to get the same number of electrons. So this first half reaction, I multiply by 3. That'll give me 12 electrons lost. And for the other half reaction, I'm going to multiply this whole thing by 4 to give me 12 electrons gained. Now I'll rewrite the new half reactants to make it a little bit cleaner before we combine it. So these are my two half reactions. I removed the electrons from them because we know we have 12 for each half reaction. We already balanced those electrons, so I just took them out. When I go to combine these half reactions, we get 18 hydroxide plus 3 selenium plus 4 chromium-3 yields 9 waters, 4 chromiums, and 3 SeO3 minus 2. And this is our fully balanced equation for this original redox reaction that takes place in a basic solution. All the steps for balancing the half reactions are the same as they would be for an acidic solution, except that I use this little trick in between of neutralizing any H pluses I add by adding an equal number of hydroxides on both sides. That wraps up our lesson on how to balance redox reactions by half reactions in a basic solution. Write down any questions you have in your notes and bring them with you to class.